Okay, we're now going to look at lecture 6 examples. Actually, we're going to look a little bit more at introducing the theory of the continuity and the Bernoulli equation. Okay. Right, continuity equation. Well, we've seen this flow equals area times velocity, and area times velocity at one point is equal to area times velocity at another point in the system. Actually, in general, this is that the flow in is equal to the flow out in a steady state system. So in this example we have here, we've got Q1 going in, it splits into two ways, and we've got Q2 out and Q3 out. And we can then say from continuity that Q1 equals Q2 plus Q3. Now we're going to use that quite consistently throughout the course and throughout all your calculations in hydraulics in practice. But so you've got an area times velocity. One going in is equal to the sum of area times velocity going out, and this works for pipes, for channels, for any closed system that we can see inlets and outlets from. Let's look at a specific example. What we'll see with this use of the continuity equation is that you can relate velocities at different points. So what we want to try and do from this example is, given the velocity going in, so we've got a V1 and a D1 area, diameter, we can calculate area 1, and from Q1 equals area 1 times velocity 1, we can then calculate the velocity coming out of the system at V2 and the velocity coming out of the system at V3. So V2 and V3. Really, that's what we're aiming to do, and that's what we can do with the continuity equation. Let's first calculate some areas. Easy to do given the diameter. We can see that the area is going to be very small, so we need to keep at least 3 significant figures on our area calculations. I'm using 4 significant figures here, so I've got the 2 areas there. I'll get the third area there, so it's convenient to do that calculation early. Start of the calculation. Calculate the flow going in, which will come out at 0.0039 meters cubed per second, or 3.9 litres per second. Always do your calculations in meters cubed per second. Now this says that 30% of the flow goes up pipe 2, so the flow in pipe 2 will be 0.3 times Q1. This comes out to be 0.00178 meters cubed per second, and using Q equals area times velocity, or velocity equals Q over A, we can calculate that the velocity in pipe 2 will be 0.937 meters per second, and thus we can work out the velocity, the flow in pipe 3, which will just be 0.7 times Q1, or Q1 minus Q2, which will come out to be 0.00275 meters cubed per second, and we can work out again the velocity 0.972 meters per second along that third pipe. We're going to look at the Bernoulli equation here. You've seen this equation in the lectures. Let's just revise these components. P over rho g. Remember that we've seen P equals rho g h. Rearrange that, we have h equals P over rho g. And that's the term, this first term in our Bernoulli equation. It's a pressure energy per unit weight. So the Bernoulli equation is equation for energy per unit weight. The first term is pressure energy. Second term here looks like half mv squared divided by m. Yep, that's the kinetic energy per unit weight. You should be familiar with that. Certainly kinetic energy anyway. And then the third term, the Z, is the potential energy per unit weight. And those are all equal to a constant, and we call that total energy per unit weight, H. So there's your Bernoulli equation made up of those three components, and they're equal to a constant. How do we apply that? We say, well, those three components are constant along a streamline. So the total energy per unit weight, or what we will also call the total head, total energy at point 1, total energy at point 1 is equal to the total energy at point 2. So we can write the Bernoulli equation like that the three components of the Bernoulli at point 1 are equal to the three components of the Bernoulli equation at point 2. Okay. What this allows us to do is to relate pressures at different points in the fluid, whereas remember the continuity equation allowed us to relate velocities at different points in the fluid, and the two together, the Bernoulli equation and continuity equation, allow us to solve many features of flows, in fact most of the flows that we'll come across. Let's have a look at an application of the Bernoulli equation for this contracting pipe. So it's flows going in here, contracting, and it flows along, and then it expands again as it goes out. We want to relate the velocity and the pressure at section 1 to the velocity and the pressure at section 2. We're going to see an application of Bernoulli doing this, trying to relate those conditions at 1 and 2. So let's say we've got a fluid of density 960 kilograms per meter cubed, flowing steadily through a pipe, so it's steady. Now remember the Bernoulli equation applies for steady flow. Section diameter, so section 1 diameter is 100 millimeters, section 2 it's 80 millimeters, so we see it's narrower, it's getting narrower. Despite what you're looking at, it's gone from wide to narrow. Okay, we don't need to worry about this narrow bit in the middle. It's gone from effectively the same as from wide to narrow, wide to narrow. Okay, so gauge pressure, right? We're given the data, we're given this value of data. We know this value P1, and it's 200 kilonewtons per meter squared, or 200,000 newtons per meter squared. And the velocity at this point at the inlet is also known as phi, and it's as 5. Now we've got the pipe being horizontal, so Z1 equals Z2, and these are going to cancel. And the question is, given these two, pressure and velocities going in, what's the pressure at point 2? We'll also work out what the velocity is at point 2. So these are our two unknowns. Solution processes. Apply a Bernoulli along a streamline between 1 and 2. So we choose a streamline, flows like that from 1 to 2, and we apply Bernoulli along it. There we are. The two Bernoulli expressions for point 1 and point 2. Horizontal, so Z1 equals Z2, we can cross those out. We know P1 and we know U1, we know rho G, we know G, we don't know P2 and we don't know U2, but let's do a rearrangement to get pressure on its own. So pressure, we rearrange this equation and we get P2 equals P1 plus this expression involving v, the velocities and the density. You should be remembering this Bernoulli equation. Remember this Bernoulli equation because we'll use it again and again. We need to work out, using the continuity equation, what the velocity at point 2 will be, and it's just area 1, velocity 1 divided by area 2. If you do your algebra, you see it's also just the two diameters, ratio of the two diameters squared times u1. That's a simple geometric calculation. This gives us a velocity 2 of 7.8. We put that in our formula for pressure we just got from the Bernoulli equation, and you do need to derive that, shouldn't be trying to remember it, and this comes out that the pressure at P2 here is 182.7 newtons per meter squared. What was it here? P1 was 200 newtons per meter squared. Let's just examine our solution. We say that at point 1 the velocity was 5 and the pressure 200. At point 2 it's gone narrower, so it's increased in velocity, but it's been squashed down and the velocity, the pressure has reduced. So velocity has increased, pressure has reduced. Velocity has increased, pressure has reduced. And this is quite a common, in fact, a feature you must remember. As a pipe contracts, then the velocity will reduce. V1 is less than V2, but the pressure, the velocity increases because V2 is greater. The velocity, the pressure will decrease. So although it looks like the flow is being squashed, so you might think the pressure would increase, if velocity goes up, pressure must go down. That's exactly what it says in the Bernoulli equation. If velocity goes up, pressure goes down. If velocity goes down, pressure goes up. Remember that feature. Why do we need to measure flow rate? Well, we always need to know flow in a channel. We always need to know flow in a pipe. We need to know flow in a duct. We need to charge they need to charge the customer. We need to know how much is being moved around. We need to know how much is leaking, etc., etc. Rivers helps us do flood prediction, what's going to happen further downstream, ensures structures, the forces on structures remain manageable. So we need to know flow. It's an absolute key thing to know in a flow, not just velocity, the actual flow rate. So in a building we need to know that you all get enough air, that we can all breathe okay, we can all be heated or cooled okay by the hot or cool air. A pitot tube is a simple flow measuring device. Actually it's a velocity measuring device, but we can convert the velocities into a flow rate, and based on the uniform flow hitting a solid blunt body, something like this. At point 2 we've got this special streamline that runs into the blunt body and stops, because at that point it has a velocity of 0. It's known as a stagnation point. The fluid is stagnant, and we can work out what the pressure is at that point by applying Bernoulli along that streamline in the centre. Remember, the V2 is equal 0 because it's stationary. We can work out what V1 is. Apply Bernoulli from point 1 and between point 1 and 2. we know the velocity 2 is 0. We saw that diagram is horizontal, so Z1 equals Z2. It's not quite right, equals 0, but it could be. This is what we have left from our Bernoulli equation, applying it from point 1 to 2. Remember U2 is 0 and we cancel the Z's. And this says that the P2 is equal to this expression. So what we say is that this is the stagnation pressure. This is the pressure that causes the fluid to stop. Pressure at stagnation point P2 in terms of U1 and P1. So this is stagnation pressure, and we'll use this quite a lot in some flow measuring devices. This is the fundamental expression used for the pitot tube, which we'll use for measuring velocity. Now, this blunt body, this thing that's stationary, doesn't have to be solid. It can be a static column of fluid, so it might be this L-shaped tube which we fill full of fluid, and as the flow flows along it, you've got some velocity going in here. It'll push the fluid up to a certain height, h2. We've measured here, so it's a sort of an L-shaped manometer. Okay, remember this. So this height here we'll call the velocity head. It's rising up to this point because it's being pushed by the velocity of the fluid. Now this pitot tube here is just giving us a pressure that is equal to well, the H comes from P equals rho GH, P over rho G. In this at this H1 point, H1, and this H2 will be V squared over 2G, the second term in the Bernoulli equation. Let's have a look at a Venturi meter. So here's our Venturi meter. What is a Venturi meter? Well, it's a narrowing of the pipe. So we're going to, as we narrow the pipe, we know that the velocity increases, and we know that the pressure decreases. And if we measure the pressure at this narrow point and the pressure upstream, we can apply the Bernoulli equation between those 2 points, and knowing the change in diameter allows us to work out the flow or the discharge in a pipe. And that's what's known as a Venturi meter. It's a narrowing of a pipe that reduces the pressure. So the trick is that we need to measure the pressure. Now we can do it with a manometer, like this arrangement. So we see this side is higher because on the manometer, because the pressure is lower at 2 than it is at 1. 1, 2. Measure the pressure, the height, the head difference between those 2 points. Here in practice are some Venturi meters. These are not using manometers. They've got a gauge pressure here, and we've got you see it goes down along here. It's narrowed, and you see how it's gone and narrowed along here. This second one's measuring it with an electronic pressure meter. But there's a Venturi meter. That's what they look like in practice. So we apply this Bernoulli equation along the streamline for points 1 to 2. Use continuity to get a relationship between U2 and U1. So that'll eliminate one of them. We'll replace U2 with that expression. Do a bit more rearranging. It's not so clever, this rearrangement, straightforward algebra, and we get something that looks a little bit unwieldy, but it's a straightforward just manipulation of the Bernoulli equation You should be able to do that if asked for, but generally we're not looking for derivations of equations. That's a straightforward manipulation. We take that velocity, multiply it by A to get a discharge, but there's also always some losses. So we multiply a coefficient by a coefficient of discharge. So here it is, CdUA, to get the flow rate. So we had velocity, we multiply by CdA1, and that gives us the actual flow. So there, just by measuring the pressure difference between the 2 points, we can work out what the flow rate is in a pipe. So very, very handy. There's an equation to use. You'd not be asked to remember that, but you would be asked to use this sort of equation. Right, if we connect a manometer, let's have a look at a manometer. If we adapt that, we go through some manometer analysis. We can a YouTube manometer analysis, we can rearrange this and we see this expression here that looks very much like the expression within that Venturi equation. So we replace this this part into here, and we get this slightly amended Venturi meter equation with a manometer. And all we need to know now is the head on the manometer and the manometric fluid density. What we don't need to know is the Z1, Z2, P1, P2. We just take one H reading and we can work out the flow. So a Venturi meter with a manometer is very, very handy. Very, very simple to device for obtaining the flow rate within a pipe. So that's the point. No elevation term Z1 or Z2. Let's look at an example. The Venturi meter is used to measure a flow of water in a 150 millimeter diameter pipe. The throat diameter, so the narrow bit, 60 millimeters, with a coefficient of discharge CD equals 0.9. If the pressure difference is measured by a manometer with 10 centimeters of mercury, what is the average velocity in the pipe? Assume the water has a density of 1000 and mercury has of kilograms per meter cubed, and mercury has a relative density of 13.6. So there's I've underlined there the specific bits of data we need to take out. Here's our equation we're going to use. Actually asks for the velocity, but there's the equation for flow. Areas, look at these, we calculate these. These are very small again, 0.0176. I've used 4 significant figures. 3 was probably sufficient. H was 0.1. Let's put these into the equation. There we go. What does this come out with? 0.0128 meters cubed per second. So 12.8 litres per second. Okay. Asked for the velocity in the question, so we need to divide that by the area, and that comes out as 0.725 meters per second. Okay, straightforward application of the equations that we derived earlier. You won't be asked to derive those equations, but understand what all the terms mean. Now there's another application of the Bernoulli equation. It's orifice flow. So an orifice is a hole in the side of a tank in this example. Here's our hole. Point 2, open to the atmosphere. We've drawn a streamline. So we've got a tank, open to the atmosphere at the top, open to the atmosphere at the hole. So the water is going to come out of this tank, whatever fluid it is, but let's think of water. We apply a streamline from 1 to 2 and apply Bernoulli along that streamline. First of all, let's just look at this what's happening at this orifice. The flow comes in and narrows slightly, and this area is the actual area, and it's slightly smaller than the area of the orifice. So we'll apply a contraction coefficient of contraction to account for this change in cross-sectional area. We'll see that later. And this narrowing of the fluid is called a vena contracta. Apply Bernoulli. Now, there's a few assumptions that might not be quite as obvious as as we might see. So here's the tank. I'll fill this with water. Fill this with water. Okay. Fluid's going to come out. That's through this hole here. It's going to flow out this way. It's going to fly from point 1 to point 2. Now the pressure here is atmospheric. Pressure here is atmospheric. So P1 equals P2. I've written them in here in these that they're 0, but if we're calculating things relative to atmospheric pressure, we can set them as 0, but P1 in fact is equal to P2. I've also said here that we've got a 0 velocity. Why is this 0 velocity? Well, let's think about what's happening here. This is moving down with a certain velocity. That's going to be very slow compared to the velocity coming out here, V2. This is V1. It's going to be very much more slower, several orders of magnitude lower than the velocity coming out of a tiny little hole. So we'll assume this. So when I've said V, I mean U. I mean U in this equation. U here. Okay. So what have we got from our Bernoulli equation? Well, left. Now here we are. We rearrange the Bernoulli equation. We apply the Bernoulli equation, rearrange it, and we get H equals U squared over 2G, which equals, if we rearrange, V over root TG. So what's this? This is quite an interesting equation. We'll see again and again. The velocity is equal to square root of 2G times the height of the fluid above the orifice. This is the velocity of the flow coming out of the hole is root 2G times root H. It's really important that the velocity is a function of the square root of the driving head. We need to account for some friction, but it'll be only slightly less than that velocity. To account for friction, we apply what we call a coefficient of velocity, some number that is slightly less than 1, typically 0.97 to 0.99. So the actual velocity is coefficient of velocity times the theoretical, which is this number, root 2gh. The discharge, the flow coming out of that hole, will be the area times the velocity. We need to account for this vena contracta. So the actual area is cc times the area of the orifice. Let's just put all that together. cc times the area of orifice times cv is the times u root 2gh. We'll call cc times cd, so cc times cv, cd. Just for coefficient of discharge, just for convenience. Okay, so we've got the actual flow coming out of the orifice is equal to CD times the area of the orifice root 2GH. That's really quite a useful calculation to be able to do. How much flow comes out of a small orifice. We could get that, how much flow comes out of a tank, depending on how deep the tank is. How much flow comes out of a reservoir, depending on how deep the reservoir is. It's going to be very similar calculation. Let's have a look at some notches and weirs now. Right, a notch. What is a notch? It's an opening in the side of a tank or a reservoir. Device for, we use it as a device for measuring discharge. A weir. What's a weir? Very similar to a notch, but at a larger scale, usually on a river, and we've got flow going over the weir. And this is definitely used for measuring discharge, and it's used for raising water levels. In this course we'll look at sharp crested weirs. Those are very similar to notches. In most rivers you'll get what's known as broad-crested weirs. They're similar analysis, but slightly more complex, so we'll avoid those in this course. Here's some pictures of some notches on rivers, and you see what they are. They're just quite coarse V shapes. Don't have to be V, they can be any shape you like, but you've got flow coming out of that, and depending on the height of the flow going over that V, we can work out the flow in the river, in the channel. So let's say that again, we measure it, take a simple depth measurement, and then we're able to calculate the flow. And we do this based on analysis with the Bernoulli equation. Here's some rather more, or one more exotic weir, curved weir like that, which we can also do similar calculations with, and a more typical weir type structure coming out of a reservoir spillway with not much flow going over. But equally, we can use that to calculate the flow in that channel. Very simple device. Let's have a look at the weir, how we do the analysis. So I've drawn a streamline here. So we've got a free surface. So let's just explain this. Right, we've got a free surface flow here going over there. It flows over the weir. We might get a bit of air here. We're not so bothered about that. What we're interested in is this streamline, and it flows from the free surface upstream to where it flows over the weir at some depth h. So we're interested in this height h above the point 1, well, it's slightly below 1, and h is z1 minus z2, will be positive. We'll apply Bernoulli equation along this streamline, and we're going to put some approximations in. So we're saying that we're going to say an approximation that this velocity at point 1 is very slow compared to the velocity going over the weir. We're also that sort of similar assumption that the kinetic energy, the U1, is very small. So we'll cross that out and say it's small. Okay. I've crossed out here the two pressure terms because they're both open to the atmosphere, so they're both atmospheric. Anything open to the atmosphere, it's atmospheric. So we cross those two out because they're equal. So what have we got now? We've got Z1 and Z2. We know that Z1 Z minus Z2 is H, and we've got a U squared over 2G, something very similar to what we got for the flow out of an orifice. So the flow at some depth over the weir is U2 is equal to root 2GH. So that's not the flow, that's the velocity. Remember, it's the velocity we've got. We're interested in the flow. So this velocity is dependent on how deep it is we go down. So we're going to do some, if we integrate this term, we're going to be able to get an average velocity, or we can work out the area times the velocity and calculate the discharge going over the weir. Right, how do we do the integration? Well, here's another closer picture of that flow over the weir at this depth h. We've got our velocity u at this depth h, it's root 2gh. And let's consider a strip, a thin strip, delta h. So delta h times the width is equal to the area. So delta h times the width is equal to the area times the velocity, gives us what we'll call delta q. Now if we integrate this over the shape between what I might call 0 and capital H, then we can calculate a value of q. So how does that equation look like? That's just the same as the last equation integrated. Here's our root h there, written as h to the half. What's different for every single different channel, weir, is that b, the width, will change. So for a triangle, b is here at this depth, b is here, but we can write an equation for b for every different shape. For a rectangle, b will be constant as we integrate. So b is the key thing that is changing for different weirs. Let's look at a rectangular weir. I've just said b does not change at all. It's equal to b, lowercase b is uppercase b. Substitute into our general equation. There's our general weir equation which we've just seen. We'll integrate that simply. Q theoretical is 2/3 b root 2g capital H to the 3/2 of 1.5. So this is the weir equation for a rectangular weir, obtained directly from the Bernoulli equation and an integration. Actual discharge, well, we need to just add a coefficient of discharge onto the same equation. Multiply, not add, of course. Put in a coefficient of discharge onto the same equation, and that gives us the actual flow. Coefficient of discharge will be about 0.9, 0.8. A V-notch weir, slightly different. We need to use the general weir equation, but we need an expression for B, this width, how that changes with H. And here I've written down the equation. You don't need to remember it, but you could work it out. It's straightforward geometry. Okay, you can do that as an exercise for yourself, but I will put this expression into our integral equation. So there it is, written into the integral equation. I've put the constants out to the left of the integration, and to the right we've got the h values. Integrate that, and here we get 8/15 root 2g tan θ/2 h to the 5/2 this time instead of 3/2. Add in a coefficient of discharge, that's multiplied by a CD, and we get this expression for a flow over a V-notch weir. And you again don't need to know how to derive this equation, but understand where it has come from and know how to use it. Let's have a look at this example. So we've got a 90-degree V-notch. Here we are. Happens to be 90 degrees, right angles. Flows into a tank with a cross-section area of 0.6. After 30 seconds, the depth of the water in the tank is 1.5 meters. So we can now work out the flow rate into that tank. it's the volume is equal to 0.6 times 1.5 and meters cubed per second, and the time is equal to 30 seconds, so we can work out the volume, for the flow rate. Q equals vol over time, which equals, well, we'll work that out in a moment. If the discharge coefficient of the weir CD equals 0.8, what is the height of the water above the weir crest? Well, we've got that V-notch weir equation. We're going to apply the V-notch weir equation. Here's our calculation for the volume and the flow rate. 0.03 meters cubed per second. Our weir equation. CD of 0.9. We know what we know everything in this equation. We know Q, CD, G, theta, and we don't know what H is. So we rearranged for H to 5 over 2. Fiddly calculation, but that comes out to be H equals 0.191. So nearly 20 centimeters to give us that flow of 0.03 meters cubed per second. Just a bit of algebra really, once we understand what the H is and how that relates. Measuring flow with a weir. The weir equation relates the height head above the crest of the weir and the discharge. We know, if we know the equation for a particular weir, and it'll be similar to either the rectangular weir or the V-notch weir, then we measure H. We just measure one single H, one single depth, and we can find the Q. It's simple. So weirs are really simple flow measuring devices and very commonly used on rivers. You'll see rulers next to rivers next to weirs in rivers if you go looking. Very common. And there's one. This is a river measuring the height. So this is not very high. It's 1 or 2 centimeters. But once the flow is up at this height, they're very interested in how much flow is going over this weir and down the channel. Not so much interested at the moment when it's not very high flow rates. But all this is got from just measuring the scale on this ruler and in the weir equation. For each weir you could draw a discharge curve, a height discharge curve. Now this is quite common. There's a couple of different ones on here. You can look at those and see how they vary very slightly. But the point being in here that as height increases, so does depth. Discharge, sorry. As depth increases, so does discharge. And here are some key points of the Bernoulli equation and what we've seen in these classes. We apply the Bernoulli equation to steady flow along a streamline. We know that the Bernoulli equation is used with continuity to do some analysis, and this is the equation that we apply. P over OG plus U squared over 2G plus Z equals H here equals a constant. So apply that at one point and it's equal to the conditions at another point along that streamline. And we've seen a pitot-static tube, a Venturi meter, a rectangular and V-notch weirs. Know how to apply those derived equations. We don't really need you to understand the derivation of those equations, or understand it but not be able to reproduce the derivations, but we really want you to use those equations. Okay, thank you.